When NASA's Voyager 2 spacecraft reached Uranus in 1986, it was winter in the planet's southern hemisphere and spring in the north. And because the probe arrived in January, most of the data it returned home to Earth that year came from the south. But the mission had only planned for a flyby, not an extended study. So by the time Voyager 2 moved on to its next target, Jupiter, Uranus' northern half was still shrouded in mystery. 37 years later, it remains that way. What secrets could this unexplored region be hiding? We sent our writer Amy M. Williams to the Jet Propulsion Laboratory at Caltech to sift through the clues. First, some background. Uranus is tilted on its side relative to the Sun. So when the Voyager spacecraft arrived at the planet, its southern hemisphere was bathed in sunlight and its north was plunged into darkness. Because of this, the probe only got a brief glimpse of the northern hemisphere during its 11 days at Uranus. It managed to snap just 3 photos of the region before it disappeared over the limb or edge of the planet. These images revealed vast, dark, flat plains and hints of strange bright spots. But since then, no spacecraft has visited Uranus, let alone spent time watching it. Voyager 2 wasn't designed to stay. Its primary mission was to take pictures and make some measurements while passing by and then move on to study Jupiter. It only made to close passes of Uranus 50,000 kilometers from the planet center during the first pass and 80,000 kilometers during the second. In comparison, Voyager 1 passed by its larger sibling Saturn more than twice as close. That gave scientists back on Earth just 2 weeks of intensive observations in which they could watch Uranus rotate almost completely from pole to pole. This observation period also coincided with Uranus's equinox, meaning that all locations on the planet received roughly the same amount of sunlight. As a result, most of the views returned by Voyager showed middle latitudes around the equator. And because the spacecraft flew by quickly, it didn't get a chance to see much of either pole. So what does this mean for the half of Uranus we haven't seen? To answer that question, we need to understand how planetary exploration usually works. Missions are carefully planned out in advance so that when a spacecraft reaches its target, it can begin making observations right away. For example, NASA's Cassini orbiter studied Saturn for 13 years, arriving at the ringed planet in 2004 and making discoveries about its atmosphere, its rings, and its moons until it was finally decommissioned in 2017. But this careful planning is difficult when your target is a sideways planet. For any spacecraft approaching Uranus, there are only 2 paths that allow for close-up observations, one in the southern hemisphere and one in the northern hemisphere. If you choose the south, you won't see much of the north at all. And if you choose the north, well, you're in for a very long wait. When the Voyager team selected their flyby path in the early 1970s, they chose the southern hemisphere because they expected the weather there to be relatively calm and because they wanted to have enough fuel left over to visit Neptune after they finished observing Uranus. They definitely made the right call. The views they got of the southern hemisphere revealed dynamic storms, clouds, and a surprisingly dynamic atmosphere. Scientists were able to use these observations to learn more about the planet's atmosphere, climate, and magnetic field. They discovered that Uranus has a very fast equatorial wind that whips around the planet in just 5.5 days. And they learned that the planet's atmosphere cools dramatically as you go higher up, possibly due to the unusual tilt of its axis. But the southern hemisphere isn't the whole story. There is a lot we do and know about Uranus because of the limited data we have from the north. And this lack of information means that we have a lot of questions that we're eager to answer. Like, why do the poles seem so different from the equator? Why doesn't Uranus's atmosphere look like Jupiter's? And what are those mysterious bright spots? One of the challenges of answering these questions is that Uranus is very far away. Signals sent from Earth to Uranus take an hour and 15 minutes to reach their destination, and the replies take just as long to arrive back on Earth, so communicating with a spacecraft at Uranus is slow going. And to make things more challenging, Uranus is sideways. That means that getting a craft into the right position to observe the northern hemisphere would take months or even years. Then, once the spacecraft arrived, it would only have a few weeks to collect data during the time that its orbit took it close to the northern hemisphere. During the rest of its orbit, communication with the spacecraft would be impossible. So, if the main goal of the mission was to study the North, it would have to be planned with great care. And that led to a lot of debate over the years about whether studying the northern hemisphere is worth the effort. A mission to Uranus would probably take at least 12 years to reach the planet, and then another 10 years to complete all of its science goals. And that's a lot of time and money to spend on one planet, especially when there are other potentially interesting places to explore in our solar system, like Saturn's moon Titan, which has lakes of liquid methane on its surface. But considering that Uranus is the only planet in the solar system that hasn't been explored by a spacecraft, it may be worth the wait. And fortunately, we already have some clues as to what we might find in the unexplored northern hemisphere. Back in 2014, a team of astronomers used a computer model to simulate Uranus' atmosphere and predict what it might look like from the poles. The results were surprising. The models suggested that high-altitude clouds over the poles are made of methane that has frozen into a form of ice called diamond dust. The diamonds would be humongous, up to several microns wide, which is about 10 million times larger than the width of a soccer ball. These particles would form cirrus clouds similar to the ones we have here on Earth, and this discovery could help scientists better understand the swings in temperature that the atmosphere experiences as Uranus rotates. Of course, we can't confirm this until we actually see the northern hemisphere, and the team hopes that a future mission to Uranus will include a probe equipped with a visible light camera that can capture images of the upper atmosphere. But the good news is that this technology already exists. NASA's retired space shuttle program included the Space Imaging and Research Telescope, which captured images in visible light. And there are plans to modernize the instrument and mount it on a future mission to observe the northern hemisphere of Uranus. Until then, the only way we can explore the unexplored is by studying the data we have, searching for clues that can tell us what's hiding in the half of Uranus that we haven't seen yet. And it's not always easy. For example, understanding the bright spots that mar Uranus's otherwise dark atmosphere has proven to be a challenge. Scientists think the spots reflect light from deeper in the atmosphere where it's less cold. But they don't know exactly what the spots are made of or how they form. Luckily, the data doesn't stop with Voyager 2. Since the 1980s, astronomers have used powerful ground-based telescopes on Earth to track changes in Uranus's atmosphere over time. In the last decade or so, they've discovered more than a dozen bright spots, watched them change location, and even seen them come and go. One bright spot in particular has captured their attention. It first appeared in 2014 and then disappeared 2 years later. But in 2020, it came back with a vengeance, growing in size and brightness and remaining that way for almost 2 years. The leading theory for these spots is that they form when gases expand from deep inside Uranus and push up through the atmosphere. But scientists aren't sure if that's true. Again, they'd love to have more data to work with. That goes for the entire northern hemisphere. Studying this unexplored region will give scientists an unprecedented view of Uranus's atmosphere and its interior. Like the seasons changing here on Earth, Uranus's atmosphere changes dramatically over the course of its 84-year orbit around the Sun. So what happens in the north may be very different from what we've seen in the south. That's because the internal heat coming from Uranus' core may influence the atmosphere differently depending on the planet's orientation towards the Sun. So the northern hemisphere could reveal important information about the structure of Uranus' core and how it interacts with the rest of the planet. In addition, researchers hope to study the planet's rings in greater detail. Discovered by the Voyager spacecraft in 1977, Uranus has more than a dozen known rings that are intermediate in complexity, halfway between the more extensive set around Saturn and the simpler rings found around Jupiter and Neptune. Some of Uranus's rings are only a few miles wide and hundreds of miles long. And despite being only a few miles across, they're opaque and visible from Earth with a good telescope. Scientists think each ring is made of countless small pieces of ice. But the exact origin of these rings is still unknown. Did they form at the same time as Uranus, or are they relatively new arrivals? Are they the remnants of something that once orbited Uranus but broke apart? Exploring the planet's rings and their interaction with its atmosphere will help researchers better understand how they formed and evolved. There's even the possibility of discovering something completely unexpected, like a moon that's large enough to be considered its own planet. Currently, Uranus has 27 known moons, but in 2012, one of those moons, nicknamed Hippocamp by the discoverers, was reclassified as a large boulder riding on the edge of the planet's rings. At the time, the reclassification shocked the scientific community. Was Hippocamp a moon? Was it a piece of debris? Or was it something else entirely? Researchers are still trying to figure it out. And it could turn out that the boundary between a moon and a rock is even blurrier than we thought. It's these kinds of mysteries that keep the scientific community hopeful that exploring the northern hemisphere of Uranus will be worth the time and expense. And there are plenty of reasons to want to return to this icy giant. If we can unravel the secrets of its atmosphere and rings, we'll better understand how planets form and evolve. And who knows what else we might find along